Welcome back. So, in the last few classes we have discussed about gas turbine combustors, in particular aerospace gas turbine combustors. Okay. And we have seen how the different parts are connected together, like how diffuser, the combustor liner, all those things are connected, and how the flow is essentially split into the primary zone, into the dilution zone, etc., and which eventually determines the final temperature profile that goes into the turbine. Okay. But as such, the main thing was that the temperature profile at the exit of the combustor is of very high importance, and as such the maximum temperature, though is useful towards though we want to maximize the temperature because that causes increase in the cycle efficiency, that is essentially limited by the material properties and the coating properties of the turbine blades. Okay. As such, as a result of that, in the combustor, the overall fuel air the actual fuel air ratio divided by the stoichiometric fuel air ratio, which is the equivalence ratio, the overall equivalence ratio remains very lean, 0.3 to 0.4, something like that, and the air fuel ratios are always very high, much higher than the stoichiometric values. Okay. So, as a result, there is a lot of oxidizer, lot of air still left, and which can be utilized for further burning. Okay. But the reason why we cannot burn more fuel inside the combustor is that if we burn more fuel inside the combustor, then the temperature that will be approach the stoichiometric adiabatic flame temperature, and that is not acceptable by the turbine blades. So, even though there is air present, excess air present inside the gas turbine, main gas turbine combustor, you cannot utilize that, because your turbine inlet temperature or the turbine entry temperature is limited by the material properties. So, there is a lot of air. So, the question is that in cases where you need extra thrust, suppose you are using a military gas turbine, you are designing an engine, a gas turbine engine for military applications. Okay. So, where the aircraft might need to accelerate, might need to take sharp turns, might need to climb up in very rapidly. So, you need all these maneuvers, all these like extravagant maneuvers needs extra thrust. Okay. So, what one can do is that one can utilize this excess air that goes out of the gas turbine engine and burn fuel in this excess air after this excess air comes out of the turbine. Alright. So, that is what exactly the purpose of an afterburner. So, the afterburner essentially as you see, the afterburners are essentially is a long pipe which contains the air that goes out of the your turbines, and you dump fuel in there. Okay, you spray fuel in there and you essentially burn the fuel there, and you generate extra thrust by accelerating the hot gases that comes out through a nozzle. Okay. So, that is what an afterburner does, and but the thing is that here this the flow that the afterburner encounters comes out of the turbine. Okay. So, it is already expanded. So, as a result, on one hand it is vitiated, that it contains some amount of combustion products that comes out of the gas turbine engine, and on the other hand it is also the flow velocities are higher. So, one big challenge in these afterburners is flame stabilization, and even more so because you are using this afterburners in kind of short intervals where the flame where the aircraft can accelerate. So, the acceleration in the aircraft can also cause acceleration in the airflow inside the afterburner. So, the afterburner sees a stringent conditions in terms of flame stabilizations. So, in this topic, in this module, what we will look into is that we will look into understanding flame stabilization and blow off in prototypical afterburners and using laser diagnostics. So, this module is rather unique. This next 3-4 classes that we will go through is rather unique because it does not really it talks about many things. It essentially tries to understand a very important combustion problem, that is flame stabilization, okay, and blow off in this kind of a rather prototypical configuration, in a practical kind of configuration using laser based diagnostics. Okay. So, here we are going to introduce this cutting edge diagnostic techniques called laser diagnostics, in particular laser induced fluorescence and particle image velocimetry, which can be utilized towards understanding some particular phenomena that happens in a practical engine. So, this course essentially will cover many things, but I hope you will enjoy this course, because as such this class will cover many things, because on one hand we will talking about a practical system, on the other hand we will talking about a practical problem, because flame stabilization and blow off is indeed a practical problem in the afterburner, and then we will attack that problem. We will try to understand that problem using this experimentations, laser based diagnostics, and we will show you that how this complex engine condition can be simplified into smaller configurations in an experiment, in a laboratory experiment, and then once we develop some understanding of that laboratory experiment, we can construct bigger facilities in which we try to understand this thing. So, this will be like an amalgamation of different things like practical engines, afterburners, laser based diagnostics, so as such and blow off experiments in small scale burner and blow off experiments in prototypical combustor. So, this is we will try to cover quite a few ground here, and this will be of a little bit different taste than what we have done before, but also here as such in this whole course we have never compromised on the rigor. We have always done deeper analysis by in a simplified system. We will also do that same thing, that is we will try to instead of just describing that to do laser induced fluorescence you need a laser, you need a camera, etc. We will tell you what is the principle behind laser induced fluorescence, so that we develop this concepts from a very fundamental viewpoint. Okay. So, here is the outline. Okay. So, so first we will go about this flame stabilization as such, which is a very rich topic in and it has been studied by combustion research for decades, and you will see that the flame stabilization is indeed involves quite a few things. It indeed involves like understanding will involve like you have to understand how combustion happens in a practical flow. Okay. That is typically we used flames are essentially stabilized in shear layers. So, on one hand we will need to understand properties of shear layers like different kinds of vortex shedding, when the vortex shedding that can happen in a reacting flow, vortex shedding that happens in a non-reacting flow. Okay. And then we will look into the properties of the flames. We will see how flame speed changes with different conditions, and how flames can extinguish by stretch rates, etc. So, it is a combination of many things, and as such all this understanding of combustion that we have developed so far will essentially feed into this this topic. So, many things will essentially goes into successful flame stabilization, and that is the purpose of this this few lectures. And then the outline is that we will go into look into afterburners, because that is the practical application that we have in mind in flame stabilization. Of course, flame stabilization, you have to understand that flame stabilization is a very important requirement in high speed propulsion systems, in ramjets and scramjets. Okay. So, those configurations might be a little bit different, because in a scramjet for example you use you have to stabilize the flame in a supersonic flow. So, fundamentally there can be some differences, but still the understanding that developed here will go a long way in describing those phenomena as well, as we will see later. Okay. So, then first we will go into afterburners, and then we will go into laser diagnostics, principles of laser based diagnostics, how do we do what is the fundamental principle behind laser induced fluorescence, and how do we do laser induced fluorescence, and then we will go into look into bluff body stabilized flames. We will assess the development in the field for the last say 50 years in a very brief review, and then we will go into the recent works by Lewin's group in Georgia Tech, and then we will go into our works at University of Connecticut from Serijan's group, where we will use chemiluminescence imaging and PIV and PLIF, etc. And then we will also focus on some of these works using a high speed PIV PLIF. And then we will go into understand force blow off and blow off in vitiated flows. Okay. So, then we will look into also blow off in Swall stabilized flames, once again from Georgia Tech as well as from DLR group. Okay. So, these are the topics that we will cover, but this is of course outline is a overall outline, and we will spend quite some time on laser based diagnostics to understand what are the fundamental principles behind it, because here we will talk about an unique situation where we will use these diagnostics to essentially solve a particular problem that we encounter in combustion. So, we will solve how basically flame blows off using this laser based diagnostics. So, and that how this flame blows up in a prototypical afterburner configuration. So, that is the whole aim of this talk. So, this is how afterburning turbofan jet engine looks like. So, the previous jet engine that we had shown you that the turbojet engine was essentially was an engine with which did not have this part. Okay, so, which did not have this this part, if you remember. I will come to this part, but before that let me just once again describe to you. So, here you have the in the front you have the fans, and then you have the compressors, a few stages of compressors, and then here you have the combustion chamber, which we discussed so far. That is this is the main gas turbine, this is the main combustion chamber. Okay, this is the main combustion chamber, and this is essentially your fuel nozzle. Okay, so the fuel is injected from here, the liquid fuel comes into through here, and it is injected through here, and it is goes into a spray like this. Okay, and it is of course small, and this is your igniter, which is placed here, and then of course the hot flow goes out and hits the turbine blades and turns the turbine blade, and the turbine blades in turn rotates the compressor blades, because they are connected on the mounted on the same shaft. Okay, and now what happens? Now in an ordinary like a commercial jet engine, you just now expand the flow through a nozzle, and that is it. Okay, but here what you have is that you have this full thing which is called the afterburner. And why we need the afterburner is already described previously, that we sometimes in a situation where you need a very sharp climb, you need to where the aircraft needs to climb very quickly, where it needs some excess thrust. So, then you turn this afterburner on, which develops which burns the fuel in the oxygen rich oxygen rich vitiated air, because as you remember here the burning happens in fuel lean. So, the air that comes out here, okay, the air that comes out here is the air is essentially vitiated because it contains products. So, with lot of oxygen. Okay. So, what you do here is that the air that comes out of the turbine is essentially vitiated air. It contains products like CO2, CO, some amount of CO. It can contain, it of course contains water vapor, and it can contain some pollutants in small amounts, and but mainly it contains quite some amount of oxygen, because what you had here was fuel lean combustion. So, now what you do is that through these fuel spray bars, through these fuel bars, these are these fuel bars, you basically inject the fuel. Okay, and then these fuels, this forms a fuel air mixture here. Okay, this mixes with this fuel mixes with this fuel mixes this fuel mixes with the air here. Okay, and in these regions, and the flame essentially can be stabilized like this. Okay, these are this V gutter afterburners you see here. So, this is the flame holders essentially. These are the things of the flame holders. Okay, so these are the and the flame is in the wake region of this flame holder, this bluff body flame holder. The flame is stabilized. Okay, and then of course you expand it through a nozzle to develop the thrust. Okay. So, then we go on to this thing. So, this is how a flame in an afterburner looks like. Okay. So, of course, the aircraft is moving in this direction, and the flame, as you see, goes out here, and this is from a Kaveri engine afterburner. that you see here. So, the exact nature of the flame depends on the state of mixing, but here you see a blue flame. So, often the flame actually is quite close to a premix flame because of the sufficient distance. If there is sufficient distance between the fuel spray bars and the flame holders, then the fuel air mixing can be complete. And of course, you see this is a very vitiated, strongly vitiated, high temperature environment in itself. This is a very the fuel the liquid fuel can evaporate very quickly, and if it mixes, it can essentially burn in a close to premix mode. But of course, you will see a lot of like yellow flames coming out of the afterburners also, which shows that it is essentially in non-premix mode. So this is what we are going to study, that basically flames in afterburners. Okay. Now, so far we have studied a lot about combustion, okay, but we have not really discussed any experimental techniques to measure things in a combustion. Now, if you want to talk about measurements, the first question is that what do you want to measure in combustion? So, what is most important in combustion? As we have discussed before, in combustion is essentially stands on two pillars. One is chemical kinetics, another is fluid mechanics. Okay, so chemical kinetics essentially talks all about the different the breakdown, how essentially the fuel breaks down into smaller and smaller units, and then it essentially oxidizes to form the products through a series of elementary reactions. Okay. So, in that sense, we know that one of the most important things that we have come to learn using this chemical kinetics is the role of the intermediates, right, role of the radicals. And as you see, one of the most important intermediates in combustion is this hydroxyl radical. H is also very important, the H atom, and the O atom is also important, but hydroxyl radical is also very important. So, we can say that if the question arises that what do we experimentally, how to experimentally obtain the reactive scalar concentration, or the first question is that what do you want to measure? Suppose then we want to measure, then if we that is the case, suppose we want to measure some radicals. Okay. So, what is the most important radical? Of course, H can be a very important radical, but that is very hard to measure. O is also hard to measure. So, it is not only that you want to measure something important, it has to be measurable also. Okay. And you have to measure it in a way so that you do not disturb the flow inside the combustor. So, you cannot really have a probe, have a big probe sitting inside the combustor which distorts the flow itself. Okay. Anything you see, if I put a probe here, first of all, putting a physical probe is difficult, but even in a normal laboratory setup, if you want to put a physical probe here, this will disturb the flow. It will act like a Blowoff body, okay, and it will cause a lot of heat loss, etc. So, we want to measure things in a non-intrusive manner. That is, we do not want to put a physical probe, but by shining light and by getting some signatures, how some molecules interact with the light that we send in, we want to measure their presence. So, in a more formal language, basically we want to measure the concentration of some active radicals. Okay. We want to measure the species concentration of some reactive scalars. So, which reactive scalar do we want? As we remember that one of the most important reactions in combustion was H plus O2 going to OH plus O. Okay. This was the most important chain branching reaction that we encountered in combustion. So, one of the product of this most important reaction is OH. Okay. And let us say then one of the most important things we can measure in combustion, which will tell us something about the kinetics, something where the reaction is happening, something where the flame is, that is where the flame is located. So, if we can say that where we have a sharp increase in OH, we can say that the flame is located at that point. So, as a result of that, it is worthwhile to measure the OH concentration in a combustion environment. So, let us say we want to measure the mole fraction of OH in a given flow. Okay. So, suppose we have a Blowoff body like this, the flow is coming here, the flame is stabilized like this. So, OH will be formed somewhere. We want to measure the OH concentration. Okay. Now, how can we experimentally obtain this reactive scalar concentration? As I said, we cannot really put a physical probe inside because the environment is also harsh, and then the actual measurements are difficult to obtain. So, let us say we want to talk about now that how can we measure the concentration or the mole fraction of this hydroxyl radical using laser based diagnostics. So, that is the most important part of this class. So, if we recap that to justify why we want to measure OH, you see this was the recap, this is a recap from the chemical structure of laminar premixed flames, which we discussed several weeks ago. This was the premixed flame, and this came from detailed kinetics, and this is the temperature, and you see OH, this is the OH profile. Of course, you see that there is this is the actually the OH profile of in a hydrogen flame. So, if it is in a methane flame, the OH profile looks something like this. Okay. So, you see that what is happening here is that this we have got some for downstream we also have got OH, but the point where the OH increases sharply, okay, the point where the OH increases sharply, that can be essentially called the flame location. Okay. So, we can say that the maximum gradient of OH, okay, we can say that the maximum gradient of OH is essentially corresponds to the my start of the flame, that essentially corresponds to the flame front. So, if I can measure OH, it can tell me two important things. It can tell me of the extent of the reaction on one hand, of the most important reaction of H plus O2 going to OH plus O, and on the second hand, more importantly, it will tell me if I can identify the region where OH increases very sharply inside a flame, inside the flow. So, I can consider that contour which corresponds to the maximum gradient of OH to be essentially my flame front. Now, typically in experiments you do not have resolution of this order, that is you do not have so high resolutions in the essentially turbulent flame experiment. So, this essentially looks like like very sharply this OH essentially goes very sharply like this. Okay. So, we can essentially find out the maximum gradient of how OH is distributed in space, in essentially 2D space, and from that we can find out the location of the flame. So, using OH we can very precisely and instantaneously using OH, if we can have the OH concentration, the distribution of the OH concentration in space, in the field distribution of OH in space in a combustor, then from that we can easily find out the location of the flame. Okay. So, that is very important, and then from that we can find out how the local flow field looks like, etc., and also it will tell you how the extent of the reaction happens in this kind of environment. So, this is OH measuring OH has been a very important activity of combustion researchers for quite some time. So, let us see what is the basic principle behind OH. So, the OH we can measure the concentration of OH of the hydroxyl radical using this principle called laser induced fluorescence. It is essentially an experimental technique involving fluorescence, and what we have here is that we will use this principle of we will use this technique of laser induced fluorescence to measure the concentration or the mole fraction of OH. Now, how this is done? Okay. So, as you see here, so this let us consider that this is essentially a OH radical. Okay. This is H, this is O, and it is essentially in a like a lower energy state, lower electronic state given by E0, and this is how a potential well looks like. And in this electronic state there are like several other states of like rotational states, vibrational states, and these are the corresponding wave functions. Now, this will involve a little bit of like terms from quantum mechanics, etc. I am just using them here for the sake of completeness, but and this will in a very basic, in a very simplified manner I will try to introduce what is laser induced fluorescence. Okay. So, please bear with me, and so this is the raw vibrational this is the electronic ground state, and these are this nu double dash 0 1 2 3 these are the different vibrational states. Okay. And these are the different vibrational wave functions. So, now suppose this OH molecule is residing at a ground state at nu dash double dash equal to 0. Now, when suppose there is an incident laser that comes in light. So, the light OH absorbs the light, it goes promoted to the higher energy state, okay, and then what happens is that it interacts with the neighboring molecules or undergoes some intersystem crossings, and then it gets in that higher electronic state, it goes down to a from the higher vibrational state in the higher electronic state, it comes down to a lower vibrational state in the higher electronic state, and eventually because it is more stable at the lower electronic state, it comes down to the lower electronic state, but while coming down it emits this excess energy in form of a photon, and this photon is essentially the fluorescence. Okay. So, this is the principle of laser induced fluorescence. I will just repeat once again. So, this OH is residing at the lowest vibrational state of the lowest electronic state. Okay. Incident laser comes, OH absorbs light, promoted to a higher electronic state, intersystem crossing, goes down to the lower vibrational state, to the lower electronic state, and while doing that it emits the fluorescence. So, there are essentially this large jump that it makes, okay, and because of the large energy difference between the two electronic state, it essentially emits photon, and that photon is essentially the emitted fluorescence or the laser induced fluorescence that we are talking about. Okay. So, that photon essentially is essentially light. So, you can collect this light using a photomultiplier or using a CCD camera, and the idea is that once you know the intensity of this light, you can correlate that intensity of the light with the population of the OH radicals that was present in this ground state before it was hit with the laser. Okay. So, once again you see I will just repeat this because this is so important. So, incident laser comes. So, this is the OH radical or the OH molecule which was in the lower electronic state or the lower energy state. Laser comes in, it absorbs the light, gets promoted to higher electronic state, intersystem crossings, gets down to the lower electronic state, emits the fluorescence, and then once again comes back to the original state by intersystem crossings. Okay. So, these are not really important right now, these are different, that is the transition within the same electronic states are not important, but there are two things here. Number one, you see that this energy level in this energy coordinate is much greater than this energy level. So, the energy absorbed is greater than the energy released in terms of photon, and that is because some energy is lost in this intersystem crossings. Okay. So, as a result of that, because the emitted energy is less than the absorbed energy, the emitted wavelength in fluorescence, laser induced fluorescence, is always greater than the absorbed wavelength. Now, there are several questions that what determines that whether this OH will absorb the light and will get promoted to the higher electronic state. It is not, if you just if you have an OH formed in a flame and we shine just normal light into it, of course it is not going to absorb and show you the fluorescence. So, there are specific rules, okay, by which the OH can absorb a given light or given wavelength of a given light or OH can absorb wavelength, and basically it depends on the energy, and essentially it means it comes down to the fact that this wave function that you hear and this wave function that we hear, that they should have significant overlap. So, the promoted state wave function and the ground state wave function, if they have high overlap, then the OH is in a conducive state to absorb the photon or absorb the incident laser beam, and it can get promoted, and once it gets promoted, it's of course it will come down, and while coming down it emits the fluorescence, and if we can collect that light, and then that light we can essentially correlate it to the number of OH molecules that are present. Okay. So, one principle that we have to that is assumed in this laser induced fluorescence is essentially called the Franck-Condon principle, and it means that the time for electronic transition is much greater than the nuclear response. So, which means that the nucleus of this OH does not change or does not move while this electronic transitions happen. That is, the electronic transition is most likely to occur without changes in the position of the nuclei in the molecular entity and its environment, and the resulting state is called the Franck-Condon state, and the transition involved is a vertical transition. Otherwise, if the nucleuses are moved, during this transition happening, then this we could not have overlapped these two potential wells like this. Okay. This is just the basic principle. Now in the next class we will come down and we will come back and discuss more about this laser induced fluorescence, and quantitatively how we can extract by collecting the light from the intensity of the light, how we can tell that the intensity of the light corresponds to what mole fraction of OH, because that is the thing, right. So, essentially what it means that we have a flame, we are shining light, shining a laser light at a particular wavelength. We need to shine it at a particular wavelength, and that is why we need a laser. So, the light shines on the molecules of OH that is present inside. The OH absorbs, get promoted to an excited state, and undergoes some intersystem crossings, and then it gets demoted to this lower electronic state. And while it gets demoted, because of the energy level difference, it gives out a photon, and this photon we can collect, and by the number of photons that is being collected, which is essentially the intensity of the light, we can correlate it to the mole fraction of OH that was present at the time when this laser light hit the OH in first place. Okay. So, that is essentially the number of OH molecules, or the mole fraction of OH molecules that is present in my flame. So, that is what I want to know, and we will go into a little bit of details that how we can find that out. Okay. So, that will be done in the next class. Thank you.